Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Are we alone in the universe? I mean, it's this huge question, isn't it? Something humans have probably asked forever, looking up at the night sky.
Absolutely. It taps into something really fundamental about our place in the cosmos.
For so long, it felt, purely philosophical, or maybe just science fiction fodder. But it seems like actual scientific research is starting to weigh in, maybe giving us a more precise answer.
That's right. Recent studies are trying to model the probabilities based on what we know about planets, stars, and life itself.
And the picture that's emerging is maybe a bit surprising. Perhaps not the crowded galaxy we sometimes imagine.
It certainly suggests the odds might be steeper than we thought, especially for technological civilizations like ours.
Okay, so that's what we're exploring today. We're going to look at some really fascinating findings about, the incredible odds stacked against finding other technological civilizations just in our own galaxy, the Milky Way.
Yeah, looking at the specific conditions needed, the planetary setup, the atmosphere.
And the time scales. The almost unimaginable amounts of time involved for life, not just to appear, but to get to a technological stage.
Exactly. It's a multi-layered challenge.
So get ready, because our discussion today might just shift how you think about those little lights in the sky. We'll touch on how rare, how incredibly far away, and maybe how astonishingly old any cosmic neighbors might actually be.
It puts things in perspective.
Okay, let's unpack this then. We've all seen the movies, right? Star Trek, Star Wars. Alien civilizations, just a jump away. But when we talk about actually finding another civilization, what kind of distances, what kind of timescales are we really up against, according to this new research?
The scale is the first major hurdle. The reality, based on these models, is far more daunting than fiction suggests.
Right.
And it's not just the distance, although that's enormous. What's really fascinating, or maybe sobering, is how the sheer scale of space and time compound the challenge.
How so?
Well, it's not enough to just find life, or even evidence that life existed somewhere else, sometime else. For us to detect another technological civilization, they need to be existing concurrently with us right now.
Ah, okay. So they can't be long gone, and they can't be millions of years in the future. They have to overlap with our tiny window of technological existence.
Precisely, and that is a huge constraint. So when we delve into the numbers from recent studies, they give us some estimates.
Let's hear them.
Okay, so the estimate for the closest technological species to us in the entire Milky Way galaxy could be as far as 33,000 light years away.
33,000 light years.
33,000 light years, yeah.
Wow. Okay, put that in perspective for us. How far is that, really?
Well, think about this. Our own solar system is roughly 27,000 light years from the center of the Milky Way.
Okay.
So 33,000 light years means... it means our nearest technological neighbors could easily be on the other side of the galaxy from us.
The other side. So not just a different neighborhood, but a whole different continent, cosmically speaking.
Yeah. Exactly. Imagine trying to shout across a continent and hoping someone hears you now, not 10,000 years ago. Light itself takes 33,000 years to make that journey.
So any signal we send takes that long to get there, and any signal they send takes that long to get here. Communication isn't exactly real time.
Not even close. It's profoundly ancient by the time it arrives. It really paints a picture of potentially extreme isolation, even within our own galaxy.
Okay, 33,000 light years. That distance alone is mind-boggling. But then you mentioned this concurrency thing. They have to be there now. How does that layer on top?
That's where it gets even trickier, because for a civilization to exist at the same time as us, even across that vast distance, it needs to be incredibly long-lived.
Right, because they had to start existing long enough ago for their light or signals to reach us now, and they have to still be existing.
Exactly. And this research, using planetary models and astrophysical data, tries to estimate how long-lived they'd need to be. The minimum suggested survival time is 280,000 years.
280,000 years, minimum.
Minimum. And potentially millions of years.
Millions.
Yeah.
For a technological civilization to survive.
Yes. Think about what that implies. A species evolves intelligence, develops technology, and then manages to sustain itself, its society, its technology for hundreds of thousands, maybe millions of years.
Compared to us.
Yeah.
I mean, how long have we been technological? a few centuries since the Industrial Revolution, maybe a few millennia with writing and cities.
It's a blink of an eye in comparison. To imagine a civilization lasting for, say, 280,000 years or 10 million years requires contemplating a level of stability, resilience, resource management, problem solving on a scale we can barely conceive of.
It suggests they would have had to overcome challenges we haven't even faced yet, or are maybe facing right now.
Precisely. It's not just about finding life. It's about finding a civilization that has somehow mastered long-term survival against cosmic and potentially self-inflicted threats.
No, it's like,
well, it's a profound constraint.
So it really hammers home that this isn't just a spatial search, looking for a needle in a cosmic haystack. It's also a temporal one, a needle that might have existed ages ago, or might exist ages from now, or is maybe on the completely other side of the haystack right now, but has to have been there for an incredibly long time.
That's a good way to put it. Concurrent existence is the key, and it demands exceptional longevity.
Okay, so let's zoom in a bit. Forget the vast distances and times for a moment. What about the place itself, the planet? What makes a planet even capable of hosting such a long-lived civilization? It can't just be any random planet, surely. What's the recipe?
No, absolutely not. And you've hit on the next crucial layer. It's far more than just, say, having liquid water, although that's generally considered essential.
Right, the follow the water approach.
Yeah, but this research we're exploring today really emphasizes the strong odds against finding truly Earth-like worlds capable of supporting complex technological life over billions of years. It boils down to a few critical interconnected factors.
Like a cosmic recipe where everything has to be just right?
Exactly. Perfect measurements, perfect temperatures, perfect chemistry, all sustained for geological ages. Let's look at some of those key ingredients, starting with something quite fundamental to Earth.
Okay.
Plate tectonics.
Plate tectonics, like earthquakes and volcanoes. How does that relate to alien life?
Well, we tend to just see the surface effects, the dramatic stuff. But plate tectonics, the slow movement of continental plates, is actually vital for regulating Earth's long-term climate.
Right.
It acts like a planetary thermostat.
The thermostat? How?
It's mainly through its role in the carbon-silicate cycle. Basically, CO2 in the atmosphere dissolves in rainwater, making it slightly acidic. This rain weathers silicate rocks on land, washing dissolved carbon and minerals into the oceans.
Okay.
In the oceans, tiny organisms use some of that dissolved stuff to build shells, mostly calcium carbonate. When they die, their shells sink, forming sediment, locking away carbon on the ocean floor.
So it pulls CO2 out of the air over time.
Yes. But then plate tectonics comes in. Through subduction, where one plate slides under another, these carbon-rich sediments get dragged down into the Earth's mantle. Over millions of years, the heat and pressure release the CO2, which eventually comes back out into the atmosphere through volcanic eruptions.
Ah, so it recycles the carbon, it pulls it out when there's too much, releases it when there's too little.
Exactly. It's this incredibly slow but effective feedback loop. It prevents Earth from getting stuck in a runaway greenhouse like Venus or freezing over completely like Mars might have done. It keeps the climate relatively stable over hundreds of millions of years, which is crucial for complex life to evolve.
Wow. So plate tectonics isn't just about geology, it's about long-term habitability. But you mentioned, even with this system, there's a potential problem. A ticking clock.
Yeah, that's the intriguing part. It's a great system, but it might not be perfectly balanced forever. Over very long timescales, there seems to be a natural tendency for more CO2 to get locked away in rocks, then gets recycled back out through volcanism.
Like a slow leak in the system.
Kind of, yeah. A slow geological sequestration of CO2. And this leads to an inherent ticking clock on planetary habitability, at least for life like ours.
Oh, so?
Well, on Earth, the projections suggest that because of this slow depletion, atmospheric CO2 levels will eventually drop too low for photosynthesis, as we know it, to continue efficiently.
Photosynthesis will stop, the basis of most of our food chain.
Eventually, yes. The estimates vary, but it could be somewhere between, say, 200 million and maybe up to 1 billion years from now. Dr. Scherf, one of the researchers we're drawing on, puts it bluntly, at some point, enough carbon dioxide will be drawn from the atmosphere so that photosynthesis will stop working.
Wow. So the planet's own life support system has a kind of built-in expiry date for complex life.
For oxygen-producing photosynthesis, it seems so, and this has huge implications for finding ET. Well, if a planet doesn't have plate tectonics to regulate CO2 in the first place, it might become uninhabitable much faster. Or, even if it does, like Earth, maybe the CO2 depletion clock runs faster under different conditions. It means the window of time during which a planet can support complex life, let alone technological life, needing billions of years to evolve, might be much narrower than we thought.
So you need the geology, the thermostat.
Yep.
But even then, the fuel for life, the CO2, slowly runs out. That really emphasizes the fragility. Okay, so the geology sets the stage, regulates the climate. But what about the air itself, the atmospheric mix?
Right, because even with the right temperature regulation, the specific composition of the atmosphere is absolutely critical, not just for life to exist, but for its complexity and its potential for technology.
Okay, Earth's atmosphere is mostly nitrogen, then oxygen, tiny bit of CO2.
Yep, about 78% nitrogen, 21% oxygen, and that crucial tiny fraction of CO2, around 0.042%, which keeps us warm via the greenhouse effect.
But that CO2 level is delicate, right?
Yep. Extremely delicate. Too much CO2 and a planet overheats. Think Venus, a runaway greenhouse effect, oceans boiled away, surface hot enough to melt lead. Or maybe the atmosphere just becomes too dense and toxic for familiar life.
And too little.
Too little, and the planet freezes. It can't retain enough heat from its star, so you need that sweet spot.
So the research looked at different CO2 levels.
It did. And interestingly, it explored a scenario where a planet might have more CO2 than Earth, but could still be habitable for longer.
How would that work? Wouldn't it overheat?
Not necessarily if other factors compensate. The models suggest a planet with, say, 10% carbon dioxide, much higher than Earth's, could potentially maintain its biosphere, its capacity for life, for a staggering 4.2 billion years.
Longer than Earth's projected habitable lifespan.
Potentially, yes. But there's a catch.
Always a catch.
Right. To avoid a runaway greenhouse with that much CO2, the planet would need to be significantly farther away from its star than Earth is from the sun. Or its star would need to be dimmer, younger perhaps. The extra CO2 provides a thicker blanket, so you need less heat from the star.
Okay, so location matters, matched precisely to the atmospheric CO2.
Exactly. And contrast that 10% CO2 scenario with one having just 1% CO2. That planet's biosphere might only last a maximum of 3.1 billion years before CO2 depletion becomes critical. So the initial amount of CO2 interacting with the planet's geology and its distance from the star sets a fundamental limit on how long complex life might have to evolve.
It's such a fine-tuned system, geology, atmosphere, orbit.
Yeah.
All have to align perfectly. Okay, but you mentioned oxygen too. Obviously, we need it to breathe.
Sure.
How does that factor into the technology side?
Yes. Oxygen is fascinating because it's not just about respiration for complex animals, which definitely need higher oxygen levels than microbes. It's about something even more fundamental for technology. Fire. Studies show that if the oxygen concentration in an atmosphere drops below about 18%, you can't have open-air combustion.
Wait, really? Like a match wouldn't light?
Exactly. A match wouldn't light, wood wouldn't burn reliably in the open air, you couldn't sustain a campfire, let alone the intense heat needed for things like smelting metal in a furnace.
And without fire?
Without fire, the path to technology as we know it hits a dead end very early on. Think about it. The Bronze Age, the Iron Age, they fundamentally depended on harnessing fire to extract metals from ore and forge them into tools, weapons, structures.
No metalworking.
No metalworking, no steam engines later on, no complex machinery, probably no advanced chemistry. It's hard to even imagine building a radio telescope or a spacecraft without the foundational technology that fire enabled.
So you need enough oxygen, not just to breathe, but specifically above that 18% threshold to even get basic metallurgy off the ground, which seems like a prerequisite for any advanced tech.
Precisely. It's another critical bottleneck. The atmosphere needs enough oxygen for complex life and enough for the key tool that unlocks advanced material science. Fire.
So let me see if I've got this straight. We need a planet with plate tectonics for long-term climate stability. We need a very specific CO2 level balanced with its distance from the star to keep temperatures right and sustain photosynthesis for potentially billions of years. And we need oxygen levels high enough, probably over 18%, not just for complex animals, but crucially for fire, enabling metallurgy and technology.
That sums it up pretty well. It's an incredibly specific and likely quite fragile set of circumstances.
It really makes Earth feel, well, exceptionally fortunate. Almost impossibly so. Okay, so even if a planet somehow wins this incredible cosmic lottery and has all these conditions aligned, what's the next big hurdle for a technological civilization to actually be detectable by us?
Well, winning the planetary lottery is just stage one. Stage two is time. Specifically, the enormous amount of time it takes for technological life to evolve in the first place, and then, crucially, the time it manages to persist.
Persist, you mean survive?
Survive, yes. Survive itself, survive cosmic accidents, survive for long enough to overlap with us.
Okay. How long did it take here on Earth?
Well, our planet is about 4.5 billion years old, and technological life really only emerged in the last tiny fraction of that time. So it took roughly 4.5 billion years of evolution through countless steps and stages.
That's a huge amount of time.
It is. Think of the milestones. The origin of life itself from non-life, that's abiogenesis. Then the evolution of photosynthesis, which changed the whole atmosphere. Then the leap to multicellular life from single cells. Then complex animals, nervous systems, intelligence, tool use. Each step took hundreds of millions, sometimes billions of years.
And there's no guarantee that sequence happens everywhere or takes the same amount of time?
Absolutely not. Which brings us to longevity. The longer a technological species manages to survive after it develops technology, the greater the chance it exists at the same time as another civilization like us. This is where that idea of the great filter often comes up.
The idea that there are these huge hurdles life has to overcome.
Exactly. Maybe the filter is behind us, like the origin of life, or complex cells, meaning life itself is rare. Or maybe the filter is ahead of us, meaning that becoming technological is relatively easy, but surviving with technology for a long time is extremely hard.
And this research suggests the survival part is key.
Very key. The calculations done by Scherf and Lammer really drive this home. Remember that planet with 10% CO2, potentially habitable for 4.2 billion years?
Yeah, the one farther from its star.
Right. Even on such a potentially long-lasting, habitable world, for there to be just one other technological civilization in the Milky Way at the same time as us, that civilization would need to have survived, on average, for at least 280,000 years.
Just for one other civilization to exist concurrently.
Yes. Minimum average lifespan, 280,000 years. Think about that. Maintaining stability, avoiding self-destruction, managing resources, weathering cosmic storms for over 250,000 years.
That puts our few centuries of industrial society into perspective.
Dramatically so. And it gets even more stark if you hope for more neighbors.
How so?
For there to be, say, 10 technological civilizations existing concurrently in the galaxy right now, the calculation suggests the average lifetime of each one needs to be over 10 million years.
10 million.
Years!
Average.
As Dr. Scherf noted, the number of potential alien civilizations depends strongly upon the lifetime of a civilization. It's not just about evolving, it's about enduring. Surviving asteroid impacts, climate shifts, maybe internal conflicts, resource depletion, pandemics, you name it.
10 million years. I can barely imagine what human society might look like in 10,000 years, let alone 10 million.
Well, it suggests any civilization we do find is almost certain to be vastly older than us.
That's a very strong implication of these numbers, yes.
Yeah.
They wouldn't likely be newcomers to the technological stage. They'd be the survivors, the ones who figured out how to last for timescales that are, frankly, geological. That's a truly staggering thought. Not just aliens, but ancient aliens who've mastered longevity. It highlights this potential fragility, maybe the immense challenge of surviving your own technological advancement. Maybe that's the great filter.
It's certainly a possibility that many researchers consider. The challenge might not be intelligence, but wisdom and sustainability.
Okay, these numbers, these conditions, they paint a compelling picture. 33,000 light years away, needing to survive for maybe millions of years on a planet with incredibly specific geology and atmosphere. It makes technological life seem remarkably improbable. But science is always learning, right? How solid are these figures? Are there big unknowns?
That's a really important point, and the researchers themselves are very clear about this. These numbers, 33,000 light years, 280,000 years, minimum survival, the atmospheric thresholds based on our current best understanding of astrophysics, planetary science, geology, biology, they're robust estimates based on today's knowledge.
But not absolute certainties.
Definitely not absolutes. There are inherent uncertainties in the models, and new discoveries, especially about exoplanets and Earth's own deep history, are constantly refining our understanding. Think of these as the best, most informed calculations we can make now.
And are there factors that just aren't in the calculation yet, things we don't know enough about.
Precisely. The research explicitly acknowledges several huge factors that ideally should be included, but we simply can't quantify them reliably at the moment. They remain major unknowns, genuine cosmic mysteries.
Like what?
Well, probably the biggest one is the origin of life itself, abiogenesis. How does non-living matter become living? How often does that happen, even if conditions are perfect? We only have Earth as an example. Was it a near inevitable chemical process here or an incredibly lucky fluke? We just don't know the probability.
Right. If starting life is super rare, then even perfect planets might stay empty.
Exactly. Then there's the origin of photosynthesis, specifically oxygen-producing photosynthesis. It terraformed our planet, paving the way for complex life. How likely is that specific biochemical pathway to evolve? Are there other ways complex ecosystems can be powered? Another big unknown.
Okay. What else?
The origin of multicellular life. Earth had only single-celled life for, maybe 3 billion years? The leap to complex, coordinated, multicellular organisms like plants and animals was a huge step, maybe another major bottleneck. How often does that happen?
That's true. Life existed for ages before it got big.
And then, even if you get complex, intelligent life, there's the frequency with which intelligence develops technology of the kind we could detect. Think radio waves, large structures, atmospheric modification. Is that an inevitable path for intelligence or just one possibility? Maybe other intelligent species focus inward or develop in ways we wouldn't recognize technologically.
So maybe intelligence doesn't always lead to radio telescopes.
Maybe not. So you have these massive unknowns, abiogenesis, photosynthesis, multicellularity, the intelligence to technology leap. And how you view the probability of each of those steps really shapes your outlook.
How so?
Well, if you're an optimist, you might think each of those steps is actually fairly probable given the right conditions. If life starts easily, if photosynthesis is a common evolutionary solution, if multicellularity isn't that hard, and if intelligence naturally leads to technology, then maybe technological civilizations aren't quite as rare as the current planetary and longevity models alone suggest.
Okay, that's the optimistic take.
Right. But if you're a pessimist, or perhaps just more cautious, you might think each one of those steps is incredibly difficult, a major hurdle with a very low probability. If any of them are near impossible, then the already low numbers we've discussed could plummet even further. We could be effectively unique, or one of a vanishingly small number.
It's like a chain, and if any link has a very low chance of forming, the whole chain becomes improbable.
That's a good analogy. We're looking at this incredibly complex equation and some of the key variables. Well, there's still question marks. It gives us a framework, a powerful one, but highlights how much we still have to discover.
Yeah, it really underscores that science is a process. We have these amazing tools, these models, but the universe still holds on to some of its biggest secrets. Okay, so wrapping this up, our discussion today, looking at this scientific analysis, paints a really thought-provoking picture, doesn't it?
It really does.
Technological alien life, likely very rare, very far away, possibly incredibly ancient, all because of this precise, maybe fragile combination of planetary conditions, atmospheric balances, and the sheer difficulty of surviving for immense stretches of evolutionary and civilizational time.
That seems to be the direction the evidence is pointing, yes. A more constrained, perhaps quieter universe than we might have hoped for.
It could feel a bit lonely, that perspective.
Good. And yet, despite these odds, despite the potentially low numbers, the researchers driving this, like Dr. Scherf, are adamant about one thing, that the search must go on. His stance is clear. Although technological extraterrestrial intelligences might be rare, there is only one way to really find out, and that is by searching for it.
So the low probability doesn't mean we stop looking?
Absolutely not. The scientific imperative remains. Because think about the outcomes.
Okay.
If we keep searching with better telescopes, better techniques, and we find nothing, well, that silence becomes data. It strengthens the case for rarity, it sharpens our understanding of the specific conditions needed for life like ours, and it underscores our own potential uniqueness. That in itself is a profound scientific insight.
Finding nothing tells us something important.
Exactly, but if we search and we do find something, a clear, verifiable signal, evidence of another technological mind out there,
that would change everything.
It would arguably be the single biggest scientific breakthrough in human history. We would know, finally, definitively, that we are not alone. It would reshape our understanding of biology, of cosmology, of our own place in the universe forever.
So the search is worthwhile regardless of the outcome. Find nothing. We learn about rarity. Find something. We learn we're not alone.
That's the beauty of the scientific quest.
So what does this all mean for you listening right now, next time you look up at the stars? Does thinking about these odds, this potential rarity, make the universe feel, I don't know, emptier?
Or perhaps.
Or does it make our own existence here on Earth feel even more extraordinary, like we won an unbelievable cosmic lottery? Does it highlight the sheer improbability, the incredible chain of events, planetary, atmospheric, evolutionary, that had to happen just right for us to be here having this conversation?
It certainly gives you a different perspective on Earth.
Maybe the most profound takeaway isn't just about searching for them, but about appreciating us. Appreciating the astonishing, perhaps fragile, reality of our own technological civilization. And maybe, just maybe, realizing the immense value we should place on ensuring its continued existence. Something to think about.